Hi, and welcome back to Codex. Our speaker today is Martin Ehler from the University of Vienna. Professor Ehler is an expert in applied harmonic analysis and the mathematics of data science. Today, he'll tell us about spherical designs. Take it away, Martin.
Thanks very much for the introduction. It's a pleasure having the opportunity to talk in the seminar. Today, I would like to talk about spherical designs. Classically, this is more associated to points, but recently we have also transferred this idea to curves. And maybe in the end, I will also talk beyond curves and points, and we will see what this is supposed to mean. Importantly, I also would like to say this is a joint work with Karl-Heinz Röchenig and Clemens Karner. Okay. The audio is fine, I suppose. Okay. Yeah, so a motivational idea is that we would like to place multiple sensors on the, let's say, the surface of the Earth. Imagine you would like to measure a certain quantity. And in some sense, we already have some guess of a distribution that we really would like to measure. And so we would like to put our sensors, some static sensors, already in a way that they already follow the distribution that we are really looking for. So essentially, we really position points on the surface of the ball. And more recently, there's the idea that, of course, you can always also use a mobile sensor. And then we are in the regime of what's called mobile sampling. And there we have a mobile sensor that can follow the path of a curve that runs on the surface of the unit ball. And now the idea is that this curve in some way is supposed to follow some predefined distribution. So in some sense, with points, we would like to approximate, let's say, a density or the probability distribution on the sphere. And with a curve, we do actually the same. We would like to find a curve that follows the density of a probability distribution. Indeed, this works very well from a numerical point of view. So with some co-authors, Manuel Gräf, Sebastian Neumeier, and Gabriel Steidl, we actually did numerical approximations of probability measures using curves. And what I would like to state, well, maybe it's a little overly confident, but for the purpose of this talk, I would like to say, from a numerical point of view, everything works out nicely. We do know what to do. In quotes, of course, everything works out perfect and everything is done. It works really nice. So in the present talk, instead, I would not go into the direction of the numerical approximation, but I would like to focus on theoretical results. I'd like to have a theorem and how well can I approximate a certain probability measure by a curve in terms of a theory. And one tool that is out there is spherical T designs. So if you look at the approximation of a probability measure, okay, numerically we can do many different probability measures. But now for our theoretical purposes, let's take a step back and have a look at what I would call the easiest probability distribution on the sphere, which is just the uniform surface measure. And how well can we approximate the uniform surface measure? And in the 70s, Delzate, Goethals, and Seidel, they proposed, they came up with the name of spherical T-design points. So we are back to points at this point. So that an equal weight quadrature formula is done for all polynomials f of a total degree at most t. So in some sense, we can evaluate the integration of f over the entire sphere simply by a sum of point evaluations. And this has really opened up a large field with many different ways of numerically and also analytically constructing such finite point sets X that are T-designs and I put just a few names out there, but this page should really be covered with different names. So there has been huge research efforts over the years. And one rather elementary result in this setting is that a finite set X are T-design points. Then its cardinality is lower bounded by a constant times T to the dimension of the sphere. So if T gets bigger, you're really supposed to integrate more and more polynomials exactly. So you could argue clearly the number of points need to increase. And then there was a 20-year-old conjecture by Kova and Meyers that has been successfully verified by a famous paper by Bondarenko, Radchenko, and Wiatzowska in 2013. And they showed that, well, actually, this lower bound that we have for the cardinality of the T-design points, this lower bound can be matched. So there do exist, for all natural numbers T, there do exist T-design points whose cardinality is bounded by a constant times T to the dimension of the sphere. And over the last years, this has also been generalized into more or to other settings beyond the sphere and essentially to compact Riemannian manifolds as well. Okay. Now, the analogous concept in terms of curves is or could be the following. So assume you have a continuous, let's say piecewise smooth function from the unit interval onto the sphere. And now the path integral of this function is essentially the integration from 0 to 1 of f evaluated on the curve times the speed of the curve. And the length of the curve is then simply the path integral of the constant function 1. And then maybe a little bit more than a year ago with Charlie Werkenig, so we came up with the definition. So we say such a curve gamma from the unit interval onto the sphere is a T-design curve if the analogous equation holds for the path integral. That means I integrate over the path gamma all polynomials of total degree at most t, and I normalize it by the length, and then this is supposed to be the same as if I had integrated f onto over the entire sphere. Okay, well, that's a definition. Now, I have learned, of course, in my very early days as a mathematical student, that once you have made a new definition, you always have to make sure there is an example. Luckily, there is one very easy example, and for t equals 1, so we're just trying to integrate all polynomials of total degree at least 1. That's not very much. And then if one plays around a little bit, it's not very hard to see that any great circle on the sphere is indeed a one design curve. Okay, so for t equals 1, there is an example. These are essentially some symmetry conditions that are at work here. But also, there are also 2 and 3 design curves. Now I show you here the trace of the curve. So the 2 design curve resembles the seam of a baseball. For a 3 design curve, the curve needs to be a little longer, or at least this one is. And it's a little pathetic, but so the great circle, and then those 2. So these are the only t-design curves that we know so far that are actually smooth and simple. Simple meaning they do not have any self-intersections. And so coming up with those 2 was already surprisingly complicated. And we were also a little lucky. Okay. But for us, it's important we have examples. So the definition I made before appears to make sense, at least. And now that we have a few examples, at least, we also have a definition. Now we'd like to play the same game as has been done for t-design points. And we ask similar questions, or questions that are analogous in terms of curves. And one question could be, well, now we don't have number of points, but now we have length of the curve. So maybe there's some bound going on the length of the curve. And indeed, so again, for t-design points, there is this lower bound. So it's really essentially the cardinality of the points grow at least as t to the dimension d. While points have the cardinality, the curve has length. So of course we would expect or hope for a lower bound on the length of the curve. And indeed, this is what can be established. So a curve gamma is a t-design. Well, there is a constant c that depends on the dimension, such that any t-design curve, well, its length is lower bounded by a constant times t to the d, but now -1. Okay? Like the intuition could say, well, points are 0-dimensional, so you need 2 to the d. A curve is one-dimensional, so maybe you gain 1 exponent, and then it's a lower bound in terms of the length is t to the d -1. It turns out that for the lower bound for points can actually be derived simply by looking at the dimensions of the polynomial spaces on the sphere. For the curve, it's, I would say, a slightly more involved argument. But still, there other proofs out there that we could follow quite a bit. And eventually we used some covering and some packing arguments. And then this is the lower bound. I just would like to mention it's actually a different proof from for curves than for points. So it's not exactly the same. Yeah, it's not quite as similar as one would expect, I would say. Now that we have a lower bound, now we of course ask, what about existence? And last year we were able to check that at least for all t and for all dimensions d, there do exist t-design curves. And the length of the curve is upper bounded by a constant times t to the, and now it's essentially d squared, more or less. Which is, of course, not quite optimal because we know we are really looking for t to the d minus 1. But on the other hand, in case d equals 2, the d half cancels. And we do have a constant times t to the 2 minus 1. So that means in case d equals 2, we do obtain, or we do match the lower bound on the length. That means for the two-dimensional sphere, that means in R3, we are able to obtain a family of asymptotically optimal length curves that are t-designs. Okay. Now that's for d equals 2. The proof, I mean, we prove it for all d, but only for d equals 2, it will be an asymptotically optimal length. So let's have a look at the proof for d equals 2 only. And the idea is to start with t-design points, x. And now it's an observation that point evaluation is very closely related to integration along a circle that is centered at this point. And due to this observation, it turns out that the t-design property for the points x carry over to the integration conditions along those small circles. Which is not totally obvious, but it does work. However, this is not quite the curve we are looking for because we want to have one single continuous function, and these apparently cannot be traced by anything continuous. These are disconnected pieces. So in order to make everything connected, we need to increase the radius of these circles. And so we make them a little bigger, still not intersecting, but now, well, actually not quite, but let's pretend now they do intersect. But if they are all intersecting, now I have one continuous one-dimensional object. And this is the curve I'm looking for. And now the length of this curve is very much related to how many of these circles do I have and what's the radius of these circles. And it turns out, if you choose the right t-design points x, the radius of intersecting circles, so when you really can make sure these circles do intersect, this radius behaves like t to the minus 1, 1 over t. And we have the number of circles is, well, this is the bound that Bonarenko, Radchenko, Wierzowska achieved. This is t to the d. So the length of everything together, of all these circles, is, well, the radius, I mean, the circumference of one circle, but this is also on the order of its radius, so t to the -1 times the number of circles, and the number of circles is t to the d. So essentially, I get a curve whose length is something like t to the d times t -1 t d -1. Okay. So this, and it's all about, we were able to argue, I haven't shown you this, but there is a way to connect point evaluation with integration over the circle that is centered at this point. Okay. Now, of course, we are really interested in all d, not just d equals 2. For d equals 2, we are good. Actually, recently, Lindblad from MIT derived an existence result also for d equals 3. So there is a curve that is a sequence of curves that are t designs, and the length is lower bounded by a constant times t squared. And I think there the curve even is a simple curve and no self-intersections. But the point is that the case d at least 4 or bigger is still wide open. So these are just the first steps towards a proof for all dimensions of the sphere. Okay. What could be a reasonable idea how to construct an asymptotically optimal length curve? Well, we already started with t-design points in our proof, and we looked at circles around each point. An even more straightforward idea would be, well, if I have a t-design, I have a few points.
Well, for the scala.
Yeah.
Oh, I'm sorry. I was talking to a friend. Sorry.
Okay, this was not me. Okay. So if these, let's say these are t-design points, of course, maybe on the sphere, the first idea would be just to connect them by spherical arcs. So, and then hope for the best that this is then a t-design curve, if I had started with t-design points. Unfortunately, this usually does not work. But at least for this type of curve, we can actually verify something similar, because in approximation theory, we do not really need equality between the integration over the entire sphere and the path integral of the polynomial. Usually, approximation theorists are happy about what's called Marcinkiewicz-Zygmunt inequalities, which means they're just uniform lower and upper bounds, so that this here is essentially equivalent. And for some reasons, we square f. So in other words, if we have a curve that is a 2t design, then it satisfies Marcinkiewicz-Zygmunt inequalities actually as equalities. Well, in this approximation theory setting, we could actually also not use only the exponent 2, but let's do it a bit general. Any P norm could be used. And then it turns out that there exists a sequence of curves on the unit sphere such that for every P between 1 and infinity, the P norm over the entire sphere is equivalent to the P norm over the curve, which essentially involves the path integral of f. And so one sequence that works for all p's. And so this holds for all polynomials of total degree at most t. And the important point is now the length of this curve indeed is upper bounded by a constant times t to the d minus 1. So here we do match the lower length bound on the curve. However, we are a bit cheating because we now get inequalities. I mean, it's nice because we get these inequalities for all p, but one has to admit, okay, there are no longer equalities. We need to introduce some constants. But
Sorry, so
yeah.
for each curve, it's going to work for all p. So you have like a gamma sub t.
There's a sequence of curves, gamma t,
Uh-huh.
indexed by t. This sequence is well chosen. And this sequence, so there are this sequence works for all p.
Okay, thank you.
Not just for one. So the p, the curve does not depend on p. The curve is there, and then it works for all p. And these constants, a, b, and capital C, they only depend on the dimension. They do not depend on curves on p or anybody. Okay, so in this setting, it's formulated, there is a sequence. What I should also say is the construction of this sequence, we pick a very distinct t-design points, just like this. We connect these points by a curve, not quite like this, but in a similar fashion. And then we get this result. So it's not exactly what we prove there, but the intuition would be, well, if you connect t-design points by a curve, you get Martin-Kiewicz not inequalities, but inequalities, not equalities. Okay. Now we have discussed a little about sequences of curves, essentially derived as unions of little circles on the sphere. Of course, we should really also look for, given some fixed t, what are nice t-design curves. Because also with points, this is a huge business. There are many websites by Womersley, by Graf and Potts and so on that just list thousands of different t-design points. Some numerically, some also analytically. And now, at least I would say Harper and Pasche in 2004, I would say, translated a paper by Banai in the following way, by making actually a nice definition. And it says, well, if a finite subgroup of the orthogonal group in RD. So this is the orthogonal group in RD. Take a finite subgroup, and I call this a T-homogeneous group if I can take any x on the sphere, and I consider the orbit under the group, and then I get T-design points, no matter which x I start with. And this is actually a rather standard construction for points, that they construct T-design points by group orbits. In this case, a single orbit. There's also a whole business where they try to choose different types of orbits for certain groups, and they combine them. But we consider here groups so that it's a single orbit, and this gives us T-design points. And now we came up with the following theorem. So suppose P is, well, what's called an edge-transitive convex polytope. Let's forget about edge-transitive. Let's just say, well, we look at special convex polytopes in RD. Those polytopes, if they are nice, they come also with a nice symmetry group. That means the symmetry maps the polytope onto itself. And if this symmetry group is T-homogeneous, as stated above, then I can project the polytope's edges onto the sphere. And then those edges all together form a T-design curve. And this is essentially the generalization of what has been done for T-design points. For points, they take special convex polytopes vertices with nice symmetry groups, and then the vertices are the orbit, and therefore they are T-design points. And we extend this here to the edges of convex polytopes. And in the proof, we will see what edge-transitive really means. And I'd also like to refer to Martin Winter, and he also actually wrote his entire PhD thesis about, in one way or the other, edge-transitive convex polytopes and classifying which polytopes are edge-transitive and so on. Before I want to prove it, I would like to show you the immediate examples. Let's forget about the great circle, but let's start with this one. This is actually the regular simplex. It's 4 edges, 4 vertices, and now I connect them by an arc. So I project the actual edge onto the sphere, and then this turns out to be a 2 design. Well, because its symmetry group is nice enough, it's 2 homogeneous. And also the T-design points, or the people that construct T-design points, they already know that also, yeah, the vertices of the regular simplex, they're also a 2 design. And so, and the same happens with, so this here is the octahedron. This here is the cube. The icosahedron, and this is the dodecahedron. So these are all the regular convex polytopes in R3, and they are in fact edge-transitive. So the vertices of these objects here are T-designs with the given strength here, and also turns out the edges as well. And we can have a look at the proof. And then it will also be clear what edge transitive means. So let E1 to En denote all the edges. Then edge transitive essentially means that all these edges are just one orbit of any of the edges. So I can write, so every edge is identical. Now I take gamma I to be the geodesic arc, so it's the projection of an edge onto the surface of a sphere. Now it turns out that then all the different all these different arcs, M, they are now also a single orbit under the group, under the symmetry group. Okay. Now it turns out that I can sum up over the path integrals over all my gamma i's. And because the gamma i's are actually a single orbit, this sum can be written as 1 over the order of the group. And I simply sum over G of gamma 1. So far, so good. This is just some elementary group theory because I sum over an orbit. And now I can go further. From here, I have 1 over the group order, the sum, and now I have an integration here, and I should really write down what it means. So it's 1 over G, sum G and G. Now it's the integral from 0 to 1, f at G gamma 1 at S. But actually, because the arc, it's parameterized with constant speed, so I have to multiply the length of G gamma 1 ds. Now it turns out that the length of G gamma 1 is the same as the length of gamma 1, so this G doesn't matter. And I can go on. I rearrange the order a little bit, so I have L of gamma 1. And now I interchange summation and integration. Then I have 1 over the order of the group. Sum G and capital G. F at G gamma 1 at S ds. And now this here, this is actually the summation over spherical T-design points. Because this set here, for each S individually, these are a number of points, and by assumption, they are T-design points. It's because the group is so nice. This was the assumption. The group is T-homogeneous. So what this here really is the integral over the D-sphere of F. So what I'm left with is L of gamma 1. Integration from 0 to 1. But now it's just, it doesn't depend on S anymore. It's just the D-sphere integrated over F ds. There's no S anymore. This is just a constant. So integration from 0 to 1 of a constant is this constant. So it's L of gamma 1 times the integral of SD of f. So I have the integration of f over the entire sphere. This one here can be written as well if I move this the length onto the other side over here. This is just now, these are now the integrals over all the projected edges. And this is what I was claiming, that the polytopes edges altogether, if I'm integrating, they form a T design. Okay. So this works quite nicely. Okay. Now, one question could be also, well, now you have these examples, but they look a bit strange because they have a lot of self-intersections. Can't we find curves that do not have any self-intersections? After all, the smooth two curves that I've shown you at the very beginning, they had no self-intersections. And again, on the one hand, we like it very much. We have found three that are simple curves, so no self-intersections. And there are two designs, three designs. Yeah, and this can also be proven that these are T designs of the respective strength. In fact, they are somewhat related to simplex, an octahedron, and a cube, but one has to move around the edges, the vertices a little bit. So it's not such a simple construction, but this can be proven. However, already for 5, t equals 5, we only have candidates. So we think those guys are 5 designs. We computed them numerically, but so far it's a little pathetic, but we cannot prove this yet. And yeah, I mean, we do have a path, so we know what we have to do, but it's not 100% that this will work out. Okay. I was thinking about showing you something about here, but I would rather like to skip this and talk about something I also thought about recently. At the moment, they are called mixed spherical designs. We will see if this needs to be changed soon. So this is definitely work in progress now. And the one idea is, well, you have static sensors on the surface. So then we moved away and we looked at a mobile sensor that moves along a curve on the sphere. But somehow in the end, it doesn't make sense to throw away all these expensive static sensors that you have already bought and distributed onto the surface of the Earth or somewhere. Why not use both? Have a few static sensors that we put somewhere, as well as a mobile device that traces some curve. And as a mathematical concept, that's what at the moment is called a mixed design. That means we have points, finite set of points, as well as a curve. And now we allow the contributions of the points and the contribution of the curve to be weighted by some constant rho so that this integration is the same as you would integrate f1 over the entire sphere of all for all polynomials of total degree at most t. So in some sense, you take some points as well as a curve. Why not combining both? If this here is rho, this contribution needs to be 1 minus rho because it has to be a convex linear combination, because f could be the constant function, and then the right-hand side equals 1 because we look at normalized measures, and then this has simply, this needs to be add up to 1. So it's rho and 1 minus rho, and we can have examples. So for you can take the south pole, and if you pick a if you pick a circle at the right height, so think about here somewhere is the equator maybe. If you pick a circle at the right height, this turns out to be a 2 design or a mixed 2 design, and actually the height here is 1/3. If it's a different height, it would still be a 1 design. But for 1/3, it's a 2 design. You can also have a south pole and a very particular distinct triangle centered at the north pole. Is a 2 design. And maybe a very beautiful 3 design, a mixed 3 design, north pole, south pole, and equator. And this is really like, it has the flavor of being really the minimalistic 3 design, because the minimal, or in order to have 1 design points, you need 2 points. For instance, north pole and south pole. For a curve to have 1 design or 1 design curve, the great circle is the shortest one. And now we take the shortest curve, that's a 1 design, we take the minimal number of points that we have a 1 design, and if we combine it, we even have a 3 design. So we really gain something. And it turns out for the regular polytopes, what you could do is take the edges of the regular polytopes, put in the center of each face a point, and then we get 3 designs, 5 designs in the first row. So the separate ones, just the points and just the edges. So in this case, this would only be 2 designs. But the combination of the 3 design, here and here, as separate concepts, these would be 3 designs. And here, as separate concepts, these would be 5 designs. But if I combine edges and vertices, I go from 5 to even 9 designs. So you gain really quite a bit, and so you go from t to 2t minus 1. Okay. Yeah, this is certainly a work in progress. I'm coming to the end of my talk. So what I wanted to tell you is, so there are theoretical results that were enabling our numerical approaches for approximating probability measures by curves. Then there is the actual paper about numerical approximations of probability measures by curves. So it doesn't have to be the uniform measure, could even be others. Now we have proved something about existence of t-design curves. This is asymptotically optimal, at least for d equals 2. If we simply connect t-design points by a curve, we do not get a t-design curve, but at least we get Marcinkiewicz-Zygmunt inequalities of the asymptotically optimal length. We have shown you a way to generate a lot of examples of curves from convex polytopes, from the edges of convex polytopes. And we have applied this in some way to data analysis. Certainly as work in progress, I've shown you some ideas about mixed t-designs where we do combine points and curves. And this is, I promise, the last slide, because there are many open questions. One of the obvious one is, of course, what about the existence of t-design curves whose length is of the order constant times t to the d-1, but now d at least 4 or bigger? Then we could ask for, yeah, but what about simple curves satisfying t-design properties and so on? So you add more properties of the curve. Of course, for a fixed t, you could ask, what's actually the shortest t-design curve? So at the moment, it's just clear for t equals 1, the shortest t-design curve is a great circle. But already for t equals 2, it's not so clear anymore. And then for mixed t-designs, where you combine points and curves, of course, there are plenty of other questions to be asked. Okay, that's it, I promise. Thank you.
All right, let's smash that reaction button. And the